Hey everyone, welcome to this lesson of Coulomb's law and question applications, the chemistry edition, explained to you in teen words by your chemist teen. And you might be wondering, what even is Coulomb's law and why do we even have to know about it? Well, let me explain. First, I'll write this equation for you that you might have seen. It's F equals K Q1 times Q2 over R squared. And this is often what Coulomb's law is represented by, this equation. So let me break this equation down for you. F is electrical interaction force, and depending on the value of this electrical interaction force, it tells you how strong the attraction or repulsion is between these two particles. K is the proportionality constant, and it is always positive. Q1 and Q2 are the charges of the two particles, and they play a big impact on determining whether the force is an attraction or a repulsion type of force. R is the distance between the two particles, and so as R increases, the distance becomes further, right? And as it goes towards infinity, the force also decreases. So F and R are inversely proportional. Now that I've given you the equation to represent Coulomb's law, let me tell you the definition of it. It's the electrostatic force of attraction or repulsion between two electrically charged objects, and it's kind of like the poles of a magnet, because if you stick one North Pole to another North Pole, they're going to repel. Same if you stick the South Pole and the South Pole. This is just like the electrically charged particles, because if two particles both have like charges or the same charges, then they're bound to repel. On the other hand, if both particles have opposite charges, so one is positive and one is negative, then they will attract. So it's kind of like the North Pole and the South Pole. Now let's go back to the equation to help us explain why when there are two like charges, the forces repel. As you can see, K is always positive, Q1 is positive, and Q2 is positive. R squared will always be positive, so the electrical interaction force will be positive. This is the same for negative because negative and negative create positive. As a result, we can deduce that when force is positive, that means both the particles are repelling. Now let's look at opposite charges. So K is always positive, Q1 is positive, Q2 is negative. So when force is negative, the particles actually attract. Now let's look at one more thing about this equation. It's the last thing. And I've mentioned this before, but I think it's really important to emphasize. As R moves to infinity, the fraction becomes smaller, and this tells us as the distance widens, then force decreases. And now that I've given you an overview about coulombs, let me give you some topics where you might find coulombs. And remember that chemistry, the topics are all built off of each other, so I'll just offer you some examples. The first one is periodic trends, and commonly you'll find questions asking you, how does Coulomb's law affect this periodic trend, like ionization energy? So how is Coulomb's even related to ionization energy? Well, it's because ionization energy depends on the strength of attraction between the nucleus and the electron. And so the higher nuclear charge, the atomic radius, the smaller it is, and shielding can all have effects on ionization energy. And so the big key takeaway is to be able to compare changes in ionization energy from shell to shell and be able to explain why. Next, let's move on to lattice energy. So what is lattice energy? It tells us how strong or attracted the ions are to each other, not just in any solid, but in ionic solids. A higher lattice energy means that the solid is harder to dissociate, and the formula of lattice energy is actually derived from coulombs. Can you spot the minor changes? Well, the force changes to the measure of lattice energy. There's now the absolute value, so now just the magnitude matters, and the R becomes just R instead of squared. However, despite the differences, the charges and the distance between the two particles still matter. Like, let's say you want to know whether magnesium oxide or sodium fluoride has the higher lattice energy. You would need to compare the charges of their elements and their ionic radii to help you determine which one has the higher lattice energy. Do you notice a common thread between these examples? Coulomb's law is involved because charge and distance play a huge role in attraction and repulsion and their strength. So let's go on to the last example I have for you, where you can find Coulomb's law, and it's the photoelectron spectrum. And you might have seen this before, where binding energy is on the x-axis and the relative number of electrons on the y. It gives you a compound. And what we want to focus on is how the binding energy increases towards the nucleus. And why does this happen? Well, it's because the electrons that are closer to the nucleus have a closer distance, right? And they also don't experience that shielding effect that the further electrons have. And that's that. I hope you learned so much more about Coulomb's, and I hope you aren't repelled by it now. Happy learning from the chemist teen.